Okay, this is section 8.3a. It's all about logarithms. Now, boy, if any one section is the most important section in this entire unit, this is it. This is the basis for what we call logarithms, which is something, again, completely new and different that you've never seen or heard of before. But this won't go away. This will be in any math class you take from here on up. Okay, so first of all, the inverse of an exponential function. So remember, exponential functions are like maybe y equals 2 to the x, something like that. Or I mean, exponential just means you have exponents. Okay, so the inverse of an exponential function is called a logarithmic function. Logarithmic, logarithmic function. Okay? So the definition of a logarithmic function. Here's the idea. If you have, let's say, some number, call it b for the base, some number raised to an exponent, I'll call it x, right? X for exponent. So you got some number that's called the base, it's raised to an exponent, and that equals some answer. I'll say a for answer. Okay? An example might be, we might have 3 squared equals 9, right? I've got a base of 3, exponent of 2, and an answer of 9. Okay, well, a logarithm says I can rewrite this, okay, as a logarithm. I would say log, L-O-G. The base is a little subscript, okay? Subscript means it's kind of like lowered, right? Superscript means is like something being squared, like it's raised up. But there's this little subscript right here of whatever b is. So we would say log base b. And then right next to the word log, on the same level as the word log, is the answer. And then we say it equals the exponent, okay? Now, you're not having to understand something with this. You're just memorizing how to go from one to the other. So this tells you the order that all the numbers go. So if I were to take this specific example with 3 squared equals 9, if I were going to write that as a logarithm, I would say log, okay, the base is a little subscript. Well, up here in this 3 squared equals 9, the base was 3. So I have a little subscript right here of 3, and that's red, log base 3. And then right next to the word log on the same level is the a, the answer. So log base 3 of 9 equals the exponent, and the exponent is 2. All right? So an exponential equation can always be turned into a logarithmic equation. All right, so look down here in my little table. I've got the exponential function 5 squared equals 25. So I could write that as a logarithm. I would say log base, okay, the base is 5, so a little subscript of 5, log base 5 of the answer of 25 equals the exponent. Notice I'm just putting the numbers in the right form. Okay, on the next one, if I'm going to change it, I would say log, the base is 10, so a little subscript of 10, log base 10 of the answer equals the exponent. Again, there's nothing to understand. You're not solving anything. You're just changing the form from exponential into logarithm. Okay, I think it's very helpful if you read them the same way that I read them. So like, for example, on this first example, when you look at this logarithm, if I said, hey, read this to me, you didn't hear me say log 525 equals 2. I said log base 5 of 25 equals 2. That's exactly how you should read it. In fact, I'm going to write out those words. So for this one down here, I would say log base 10 of 1 over 100 equals -2. I mean, those are the exact words that I would say. Log, I actually use the word base in front of whatever the base is. That way, if you say it correctly, you'll remember when you say log base, oh, what number do I put here? You put the base there. Okay. I'm going over, we're going to be back and forth a lot. I'm going over to the homework page, which is page 74, and I'm looking down here at number 13. Okay, page 74, down at number 13. So notice it doesn't say to solve anything. It simply says express the equation, meaning the exponential equation, in logarithmic form. So on number 13, if I'm going to change that to a log, I would say log base, well, the base is 13, of the answer, log base 13 of 169 equals the exponent. Okay, remember, the logarithm always equals the exponent, right? The log always equals the exponent. We're going to come back to that idea later. A log always equals an exponent. So if I were you, before you do anything, I would practice right now on number 14 and 15, okay, how to write that as a logarithm. All right, so now I'm going to go back to the table that I was on. I'm going to skip that third line. I want to go to the fourth line. What if I, oh, no, I don't want that one. I want to add a line. Sorry about that. What if I have a logarithm over here, and let's say it is log base 5 of m equals n. Okay, well, what if I want to go the other direction? What if I give you the logarithm and I want you to write it in exponential form? Okay, well, which of those numbers is the base? Well, the 5 was the base, so I have a 5. Which of those numbers was the exponent? Remember how we said the log always equals the exponent? So the n is the exponent, so 5 to the n. And the only thing left is the m. I've heard some teachers say that you go in this order. You start at the base, you come around, and end up here. So it's like you start at the 5, and then to the n. So first thing I wrote down was a 5. The next thing I wrote down was the n. And then the last thing I wrote down was the m. The same thing works for going the other direction. You could say, well, if I want to change this into a log, you start right here at the 5. You come around through the 25 and back to the 2. So when I'm writing log, the first number I write is the 5. And then the next number I write is the answer. So it was the 25. And then the last number I wrote was the 2. It equals the 2. I mean, if that helps you, I don't know. Okay? So I suggest you go over to the homework page, page 73, and look at number 1. Okay, it says express the equation in exponential form. So if I'm going to write this in exponential form, I start right here at the 5. I'm going to go through the 2 and back to 25. So the base is 5. The log always equals the exponent, so it's a 5 squared equals 25. Or maybe I go to, let's go down here to number 5. All right, so I start right here at the x. All right, so the base is x, the exponent is y, and then it has to equal 5. Again, we're not solving anything, we're just changing the form. Okay, so again, I suggest you practice this on 1 through 6 to make sure you've got the idea of going back and forth. Okay. So come over to that first page again. And we are right here on this line. All right, so if I write that as a log, I would say log, let's see here, log base e of the answer, so of the square root of e, equals the exponent, so equals 1/2, right? So I just went in the same order as before. Okay, but here's the thing, anytime we have log base e, okay, that gets its own special notation. Remember how before we said e is a special number, just like pi was a special number? So a base of e gets a special notation. Instead of saying log base e, you can just say ln, and that means natural log. So anytime you see ln, that means log base e. So this could be written natural log, so that replaces this part. So the natural log of the square root of e equals 1/2. Okay, so if you look at the next line, maybe move this one. I don't want you to think it's that line. Move it down here a little bit. Okay, so if I look at this next line, if I have this logarithm, natural log of q equals n, remember there's right in here, there's this little subscript of e that's hidden, right? Because anytime you see ln, that means the base right there is e. You don't see it. So if I ask you to change it to exponential, you're going to say, all right, what was the base? Well, the base was e. What was the exponent? Remember, the log always equals the exponent, so e to the n equals, and the answer is q. Okay, so if you look over at the homework page, page 74, go down to number 16. All right, so when I look at number 16, the first thing that I see is the e. If I want to change this to a log, my thought is, now don't write, just listen for a minute. My thought is, oh, this is log base e. Oh, but as soon as you say that, remember, instead of log base e, actually you can say natural log. Okay, so natural log of the answer, so natural log of p equals, the log always equals the exponent, equals 2. And I always have students say, if we want to, can we just write log base e of p equals 2? Well, you can write that down, and then you can change it to this. You have to get familiar with this ln notation. Okay, this is just a special notation that means log base e. Okay, so try number 17. You would say, okay, log base e, but instead of saying log base e, you would just say natural log. So log base e of the answer equals the exponent. I could go the other direction, come up here to number 7. Okay, so what's the base right there that we don't see? Well, the base right there is e. So if I want to write it as an exponential, I would say e, which part is the exponent? Remember, the log always equals the exponent, so e to the first equals x. Or on number 8, what's the base? Oh, if it's an ln, I know the base is e, so e, the exponent is t, equals m. Okay, so all of 1 through 21 is just practicing going back and forth. You guys, this should tell you, if I'm having you do 21 of just practicing back and forth, you have got to understand this notation of how to go back and forth from exponential to log. If you can't do this, you can't do the whole rest of the chapter. Everything in the rest of the chapter is based on this being able to convert back and forth. Okay, so if I were you, before I even come back and listen to the rest of the notes, I would finish the homework part, the 1 through 21, just practicing going back and forth. Okay, once you've done that, then come back and let's look at page 72, and we're going to talk about some basic shortcuts. All right, so we said that the natural logarithm is when you have a base of e. So natural logarithm is like when I write natural log of x, right? We also have something called a common logarithm. A common logarithm is if your base is 10. I'm going to say here b equals 10. So you might write log base 10 of whatever. I'll say of x. How about I say equals 2? And for a common logarithm, if there's not a base written, if it just says log of x equals 2, so notice it's log, it's not ln, so we know it's not a base of e, but there's no base written, then we assume that the base is 10. Okay, it's called a common log. Just some notation. Sometimes I think you see that notation like on ACT and SAT, that kind of thing. All right, and so the last thing I want to mention before we go on to the shortcuts is what I've already said, but it's a biggie. I'm going to put a little handy-dandy star by it. Generally speaking, a log is an exponent. Okay, a log represents an exponent. The answer to a logarithm is an exponent. If I said, for example, log base 3 of 27 equals 3, that 3 is an exponent, because aren't we saying that 3 to the third equals 27? Or I could just as easily have said log base 7 of 49 equals 2. So that 2, the log equals 2, so that 2 is an exponent, because aren't I actually saying 7 squared equals 49? So logarithm always equals an exponent. Okay, so some basic shortcuts that'll save us some kind of time and effort. Remember our exponent rule when we said anything to the 0 power equals 1, right? Anything to the 0 power equals 1. Well, if I were to change that into a logarithm, I would say log, what's the base? X of the answer equals the exponent. So does it matter if x is a 10? In other words, is 10 to the 0 still equal 1? Of course it is. And if I change that to a logarithm, wouldn't I be saying log base 10, excuse me, of the answer equals 0? Well, what if, instead of a base of 10, what if I used a base of 4? Is 4 to the 0 still equal to 1? And if I wrote that as a logarithm, wouldn't I say log base 4 of 1 equals 0? So in general, the log of 1, no matter what the base, equals 0. Look at letter A. Oh, well, what if the base is e? Because natural log means a base of e. Is log base e of 1 equal to 0? Yes. Anything that has a 1 right here, any logarithm that has a 1 right here is always, always, always going to equal 0. Period. Right? The log of 1 equals 0. You've got to get that in your brain and know it forever. Okay? So we'll come back to the shortcuts in just a second. So if I look down here at some of my examples, look at number 9. If I know that a logarithm equals an exponent, so I'm trying to simplify it. In other words, I'm trying to figure out what this equals. Okay, what does this equal? Well, remember, I know that a logarithm equals an exponent. So what this is really saying is 7 to what exponent equals 49? Well, wouldn't the exponent have to be what? Wouldn't the exponent have to be a 2? Okay. I'm going to skip number 10 for just a second. Go to number 13. Okay. If I'm trying to figure out, if I want to simplify this, I know a logarithm equals an exponent. So the idea is 3 to some exponent equals 9. Well, what's the exponent on 3 so that it equals 9? Wouldn't it have to be a 2? So the logarithm equals 2. Okay. Some of them aren't as obvious. Let me see if I can find another one that's obvious. Don't help me. That's it for my obvious ones. Okay. What if it isn't so obvious? Then one thing we can think about is look for the same base. Look for the same base. Base. Okay, what I mean by that is letter A. When I see natural log, there's this little, anytime I see ln, I know there's a little subscript of e that I don't see, right? Well, do you see that that subscript that I don't see of e is the same as that e that's there that I do see? I have the same base, or on letter C. So right here I have a base of 5. This logarithm, now this logarithm is an exponent. I know it looks weird, but the logarithm has a base of 5. So I see the same base in two places. Or when I look at letter D, so the subscript is 2, so the base is 2. But then over here, I have a 2 to the x, right? So that 2 is also a base. So anytime you see the same number in there, it's always going to equal the other number. So if I see these two 2's, the answer is just going to be that x. Whenever I see those 5's that are the same, the answer is going to be whatever that x is. I see the e's that are the same, the answer is going to be whatever that x is. I see the e's that are the same, because isn't there like a little base right there of e? See the e's that are the same? The answer is going to be whatever that x is. So let's look at this as a more specific example. If I say, what is log base 3 of 3 squared? Then you would say, well, according to what we just said, I see the 3's are the same. The answer is going to be 2. Well, think about what we just said. If I have log base 3, and this is 3 squared, that's like saying 9, right? Is it true that the exponent would have to be 2 so that 3 squared equals 9? Hopefully that makes sense to you. Okay, so here's how, whoops, sorry about that. Come back. So here's how handy that exponent is now. I'm looking at this a and the b thing. So on number 1, there's a base here of e that you don't see. So anytime you see an ln next to an e, it's always just going to equal whatever that exponent is. So the natural log of e to the first is 1. Natural log of e squared is 2. Okay. Oh, what about 1 over e? Well, think of it as the natural log. Isn't 1 over e the same as e to the negative 1? Okay, so anytime you see a natural log right next to an e, it just equals the other number. So negative 1. So natural log, I'm going to kind of rewrite what I have here. The natural log of e to any power always equals that exponent. That comes up a lot. Okay? Now, what if it's written this direction, like on number 4? What if the e is down here and the natural log is in the exponent? It doesn't matter. Anytime you see e and natural log right next to each other, it always equals the other number. Okay? So look at number 5. This is similar to this letter C. I see a base of 4, another base of 4. Anytime you see the same number like that, you know the answer is always the other number. You might be saying, well, how does number 6 fit that? Well, maybe I think of this as log base 2. Isn't 8 the same as 2 cubed? And so really I have the same number right next to each other, so the answer is just 3. Now, you can think of it like that. You know, that's why the answer is 3. Or you could just look at this and you could say, well, since I know the answer to a logarithm is an exponent, 2 to what power would equal 8? And hopefully you know your cubes, and you would know that 2 to the 3rd power equals 8. Okay, so for number 7, what I actually have here is log base 5. Well, 1 over square root of 5, isn't that like having a negative exponent? Isn't that like saying 5 to the negative 1/2? Negative because it's in the denominator, 1/2 because it was square root, right? Square root means exponent of 1/2. And so now you see, hey, look, it's got those 5's that are the same. So isn't the answer just the exponent, negative 1/2? Okay. On number 8, you've got a 10. And remember what I told you on the previous page? If it's log and there's no base written, then it's an implied base of 10. So now you see the 10's are the same. And so the answer is just that other number, which is 9. Okay, so let's see how that applies down here. So you could say, well, I know the answer is an exponent, so 7 to what power equals 49? If you're not sure, just start thinking about 49. Isn't 49 the same as 7 squared? Oh, so the answer to the logarithm is the exponent. Oh, the answer is, oh, I'm sorry, I wrote that wrong. 1 over 49, right? So really you have 1 over 7 squared. Oh, but we don't want it in the denominator. So isn't that the same as 7 to the negative 2? So the log base 7 of 1 over 49 is negative 2. Why? Because the log always equals the exponent. Okay. Now don't just see the 49 and the 7 and think the answer has to be 2. Because remember what we're saying is 49 to what power equals 7? Well, what would the exponent on 49 have to be? 49 squared is not 7. But what about 49 to the 1/2? Right? Isn't the square root of 49 equal to 7? Oh, so the exponent is 1/2. Okay. So look at this one. 49 to what power gives me a 7? Well, over here we said log base 49 of 7 is 1/2, but this is 1 over 7. Oh, if it's a fraction, doesn't that mean it was in the denominator? So doesn't that mean that the exponent would have to be negative 1/2? You can always check it. Is 49 to the negative 1/2 going to equal 1/7? And you'd say, well, negative puts it in the denominator. The 1/2 means square root of 49. Yeah, that works. Okay, what about this one? 3 to what power equals 1/9? Well, the fact that it's in the denominator means my exponent is negative. 3 to what power is 9? Isn't it 3 squared? So the answer is -2. Okay, on this one, 9 to what power equals 3? Well, in order to turn 9 into a 3, wouldn't you have to take the square root? And doesn't square root mean exponent of 1/2? Okay, what about this one? So 10 to what power? 10 to what power equals 10? Well, the only way to end up with the same number is if your exponent is 1, isn't it? Okay, what about this one? 10 to what power equals 1/10? Well, I know the exponent is 1 because I want it to stay at 10, but the fact that the 10 is in the denominator means I wanted my exponent to be negative. So the exponent would be -1. Okay. Again, maybe you want to try a few, let's see, on page 75. I would say, really all the way down to 43 are kind of what we just practiced. All right, so I would practice some of those, but then you can come back and we can look at these that I'm calling next level. Okay, here's why I'm calling them next level. So here's what I'm thinking. 49 to what power? You know what? How about if I look at it this way? I'm trying to figure out what the exponent is. I'm just going to call it x because I don't know what it is. All right, so it's like saying 49 to some power, 49 to the x, equals the square root of 7, right? Okay, so let's rewrite this so that I have the same base on both sides, right? Isn't 49 actually 7 squared? Okay, so really I have 49 to the x, and on this side I actually have 7 to the 1/2, right? Okay, so when you raise a power to a power, don't you multiply? So really I have 7 to the 2x equals 7 to the 1/2. Do you see that I have the same base on both sides? I have a 7 here and I have a 7 here. Well, the only way the left can equal the right, if the base is the same, the only way these can be equal is if this exponent is the same as this exponent, right? In other words, 2x has to equal 1/2. Well, if 2x equals 1/2, could you solve for 2? Wouldn't you just divide by 2? So you would get 1/4. Okay, let's try this one. So if I don't know the answer, I'm going to say equals x. Okay, so let's think of it as exponential. So 27 to some exponent equals 9. Okay, if you can't tell, 27 to what power? If you can't tell, then get the same base on both sides. Isn't 27 a base of 3? I could write it as 3 cubed. So that 27 is being raised to the x. Over here, the 9 is 3 squared. Okay, so if I raise a power to a power, I actually have 3 to the 3x equals 3 squared. So like I said last time, if you get the same base, I got a base of 3, base of 3, the only way they can be equal is if this exponent equals this exponent. So in other words, 3x has to equal 2. Well, if I'm going to solve for x, wouldn't I just divide by 3? So wouldn't x have to equal 2/3? Okay, and just to show you that that works, what we're saying is that the exponent on 27, is 2/3, and it should equal 9. Well, let's check. Don't we do, the denominator is the root, so the cube root of 27 is 3, and 3 squared is 9. It works, right? Okay, look at number 20. So 27 to some power equals 81. Okay, well, what has a base, let's see, what would equal 27 and 81 that has the same base? I know that 27 is 3 cubed, and that 27 is being raised to the x. Let's see, can I write 81 as a base of 3? I mean, I know 81 is 9 squared. And isn't 9 3 squared? Oh, so can't I write 81 as 3 to the 4th? Okay, so I actually have 3 to the 3x equals 3 to the 4th because I have the same base. That means the exponents are equal. So 3x equals 4, which means x equals 4/3. Okay, let's try another one. So 8 to some power equals 32. Well, I know 8 is 2 cubed, so 2 to the 3rd, that 8 is being raised to the x. Can I write 32 as a base of 2? This actually came up on a previous homework. I don't know if you remember, but we said that 2 to the 5th is 32. Oh, so if they have the same base of 2, notice the exponent over here is 3x, and that has to equal the exponent over here of 5. So doesn't that mean x is 5/3? So we're getting the same base on both sides. So I've got here 0.01 to some power equals 1,000. Okay, how am I going to look at this? 0.01. 0.0, isn't 0.01 1 over 100? Right? Isn't 0.01 1 over 100? And remember, in the old days, you do your place value. This is the tenths, and this is the hundredths. So 1 over 100, and that's being raised to the x equals 1,000. Okay, 100 and 1,000, aren't those both bases of 10? So couldn't I think of, let's see, 1 over 100. So I could say 1 over 10 squared, right? But wouldn't that be like 10 to the negative 2, right? Because it's in the denominator. So 1 over 100 being raised to the x. Is 1,000 a base of 10? Sure it is. It's 10 to the 3rd. The bases of 10 are easy because you just count up the number of zeros, right? 3 zeros, so it's 10 to the 3rd. Oh, okay. Now that I have the same base, I can say this exponent, negative 2x, has to equal this exponent of 3. So x equals 3 over negative 2. Okay. A lot of examples here. How about we go to number 24? Look at number 24. So 16 to some power equals 8. Yes, I could write 16 as 4 squared, but 8 is not a base of 4, right? 4 to no power equals 8. I do know that 8 is 2 to the 3rd. Could I write 16 as a base of 2? Yeah, 16 is 2 to the 4th. And that 16 is being raised to the x. So now that I have the same base of 2, I could say this exponent of 4x has to equal this exponent of 3. So x equals 3/4. Okay, so that's the next level type problem. So in your homework, you have one page of just going back and forth. No solving, just going back and forth, practice. Then you have one page of the basic simplifying, and then you have one page of the next level simplifying. Okay.